Today we're going to go on with MATLAB and ordinary differential equations and talk more about the harmonic oscillator, some technical bookkeeping details, and maybe we'll talk about energy. I want to start with a quiz. Here's a differential equation. Here is a candidate statement about the solutions of the differential equation, that this differential equation has some non-zero solution of this form, or this form, or this form, or this form, or none of these, or more than one of these. And I don't want you to solve the equation. I want you to look at it and tell me the answer. And I'll give you, let's see, I want you to do this not in pairs, so not discussing, just do it yourself, and start voting. Uh, 10 seconds left. 5 seconds left. 3, 2, 1. Stop the vote. Let's see what we get here. Okay. Now we're going to have a second vote. So I'm just going to record that and not tell you how it goes. We're going to have a second vote, which is not the same question. Pick out one of the solutions of this equation. Any one from this list. So that's A, B, C, and D. E. Only pick E if none of these are a solution. So we want at least one solution, or none of these are a solution. 5 more seconds. 3, 2, 1. Lock up the vote. Okay, let's see what we have here. Okay. So some people think this is a solution. Some people think this is a solution. Some people think this is a solution. And some people think this is a solution. Okay, let's work on this a little bit more. We're doing the same quiz, but we're going to take item C here and cross it off. And now I want you to answer the quiz again. Find any solution, or none of those is a solution. What? How can you tell that I didn't? Does your what? Your clicker does lights to stay.
If it works, it goes green, and if it doesn't, it flashes red.
Okay, good. Let's try again. Pick out at least one solution, or E if none of them is a solution. Okay, 3 seconds left. 3, 2, 1, stop. We look at the solution. D. Okay, so the majority of you got this entirely right. So the confusion here, just for those of you who got it wrong, is that this looks disturbingly like the harmonic oscillator equation. The harmonic oscillator equation has a minus here, and then this turns to sines and cosines. If you don't understand the harmonic oscillator equation, watch the video of me walking back and forth last lecture, explaining why it is that if there's a minus sign here, you expect oscillations. With a plus here, the intuition is that if we take this point to 0, if I am x here, my acceleration is in that direction. And if I'm here, my acceleration is bigger in that direction. So that gives you the thought that we'll have exponential growth. The farther I am away, the bigger my acceleration away is, and I expect exponential growth, which is why most of you voted for C, because it just looks like exponential growth. The bigger it is, the bigger it accelerates. On the other hand, this is a second order differential equation, so you always have two solutions, just like you have sine and cosine for the harmonic oscillator. What's another solution? Well, if you go through the algebra, you find out that there's e to the t and e to the minus t. How could it be that the farther I am, the bigger the acceleration, I could get a solution which is decaying exponentially in time? Well, here's how it works. I'm over here. somebody throws me that way, and I'm going very fast, but I'm accelerating that way. So I'm going slower and slower and slower, and slower and slower and slower, and I come to a stop right here. Now, that's actually a very improbable event, because if the person who throws me doesn't throw me hard enough, I'll slow down more and more and more, and before I get there, I'll come to a stop and accelerate away. Or if they throw me too hard, they'll throw me, I'll get to here, I'll be slowing down, but I'll still be moving when I pass through 0. And then the bigger my negative value, the bigger my negative acceleration, and I'll take off that way. So the nature of the solution, the general solution, is some positive exponential, some negative exponential. You have to have just the right initial condition for there not to be at least a little bit of that positive exponential in there. So in general, this solution has exponential growth unless you throw something towards the origin at exactly the right speed. And then it will just stop. Otherwise, you throw it too fast, it'll take off through one side, through slow, it'll take off the other side. Okay, any questions about this differential equation? This is in the list from the back of the book. I forget, is it in the pamphlet or is it in the back of the book of the differential equations you should just know. So everything I just said should be comfortable and you should just know it. Okay, next I want to continue last class, which is just MATLAB and differential equations. And let me try to get the lights. $1 prize to somebody who between classes figures out a nice light combination which is not this. This is okay, but I think for some of you it's early in the morning. Some of you are sitting in the back of the room. It might be a little. Is it soporific or soporific? How do you say that word? Soporific, soporific. Is it a P or PH? Any English majors in the room? There's a word that sounds like that that means it tends to put you to sleep. Like engineering or something like that. Okay, so here's this thing I worked on last class. And to start with, of course, it looks like a blur of dizzy code. And you look at it and you go, oh my God, that's confusing. But it can't be that confusing because you understood it last class. All the green stuff is just comments, so it looks dizzying, but it has nothing in it as far as code goes. Most of the stuff up here at the top is just setting numbers equal to variables equal to values, so there's not much interesting there. In terms of like complicated logic in this program, there's just one loop here, and then MATLAB has this cute thing, you can make loops disappear. So you take that little plus sign, that line means it's hidden code. So all the logical complexity in there, which is just one loop, not so bad. And then the rest is just formatting for input and output and stuff like that. So it's not that complicated. The interesting part of the code, in terms of the mechanics part of this class, was all hidden in just a few lines. It was this line here, and here were two candidate lines, one for a harmonic oscillator and one for a particle falling through honey. Here's the particle falling through honey. Let me just go back to the harmonic oscillator since we were just talking about that. So there's one line of mechanics here. There's this is the material properties. There's one line that gives you the relationship between force and acceleration. That's F equals ma. And then there's the kinematics, that position advances with velocity. The new position is the old position plus velocity times time. And in a short interval of time, you think of the velocity as constant. And if you take shorter and shorter intervals, that's more and more true, so you get a more and more accurate solution. And then we have the new velocity, comes from the new acceleration. So here's the kinematics part. So the whole course is material properties, the laws of mechanics, and kinematics. Then we predict the future by doing this again and again and again, and that's why there's a loop here for doing it again and again and again. Now, what I added here was a little change in logic, which I almost did at the end of last class, but I ran out of time, which is last class I made an array, and every time I got a new value, I made the array longer. And this is not a mechanics thing, it's just the details of MATLAB, that MATLAB has a memory allocation problem. It's such a big problem that they call it, Cleve Moeller, who invented MATLAB, gave a talk at Cornell, and people were complaining about how slow MATLAB was compared to C. And he goes, yes, we have a memlock problem, which means memory allocation problem. It's such a big deal. Everybody at MATLAB do memlock. That's an issue. So it's got a memlock problem, memory allocation. Every time if you store an array, then you make the array a longer list by 1. It has to figure out where to put it again and again. In last class, remember, I tried to do a calculation that just took too long. How do you avoid that problem? Again, this is just MATLAB syntax. Different languages are different in this regard. But you avoid that problem by setting aside space for the variable. So we know that we're going to calculate n values here. Actually, it was n intervals of time. But if we have the start and the end, that means n plus 1 values. So we store a set of zeros where we're going to store all those n plus 1 values for the time. The initial time, h, then 2h, then 3h, then 4h, all the way up to nh, and that's n plus 1 numbers. And there's a command in MATLAB that says fill in an array with zeros. Here it says fill it in with 1 row and n plus 1 columns. For this calculation, it doesn't matter if we use rows or columns or rows. And then we fill in some zeros here for x. We fill in some zeros here for v. And then instead of appending to the array and making it longer and longer, we just put in the new values every time we calculate them. So we're going to be running this crystal ball, predicting the future. We set aside first all the places we're going to store the values of the time and x and position. And then as we predict the future, we fill in the numbers as we do the prediction, one time each as we go through the loop. Okay, so now if I do this calculation, I, with luck, somewhere, what did I do? I started iClicker. Okay, I told you I was senile. Okay. Okay, so we get our sine wave back again, and we also got an error. Let's see. Size vector should be a row vector with an integer number of elements, row vectors, and test 1 at line 21. What didn't it like? Size should be a row vector. N plus 1 is an integer. Okay, so let's just take care of that problem and say n is equal to floor of n. Okay, see if it likes that better, and see if we get it still to get the nice plot. Okay, in both cases, it doesn't quite end maybe exactly at the right place, because when we divided that up, well, it actually should be about the right place, but it doesn't, maybe not exactly the right place. Okay, any questions about the graph, the solution, the method, MATLAB? Okay, so what you should be thinking to yourself is, if Professor Ruina left the class right now, he got run over by a truck. After I was done grieving, could I write this code again myself without anybody's help? Okay, so if you could not, then you should then please do other people in the room a favor and ask what it is which would stop you. It would probably stop other people as well. Yes?
Did you just fix the T1 being T5 for fun, or is there anything for that?
Yes and no. I picked the 2 pi because this differential equation that I put here, this is the harmonic oscillator equation. I picked a spring constant of 1. I picked a mass of 1. So the square root of k over m was 1. So the solution of the differential equation in closed form, in analytic form, is cosine of t. So I picked 2 pi, so I get just exactly 1 cosine wave. But in terms of what we can look at here, I can now I can get away with bigger numbers, like 100 pi, and run this again. And it looks like you can't even see through the blur of what's happening there. If I want to make that not such a mess, I can see what I did is I plotted here a green star, so it made it fat. So I can make it a little thinner by just making it green. I think that will work. And now you can see the sine waves in there. And you see these exponentially growing sine wave oscillations, which is what we expect from the solution of this differential equation. Not. Right? This is a harmonic oscillator equation. It's not supposed to do that. This is a numerical error. Remember, this is just doing a numerical approximation of the solution. So as I said last time, we can spend more money, 10 times more money. So now we're doing 1,000 time steps per second, and we're running this for 300 seconds. So we're asking MATLAB to go through this loop 300,000 times. And we ask it to go through the loop 300,000 times. And it has to think about it for a while. Hopefully not too long. Come back. Stopped in debugger. So we debugger this thing. What? Do I have to step it? Where am I here? Oh, yeah. Now this is db quit. If you get stuck here and you actually enter the debugger, which is a very nice thing I've been told, but I'm not very comfortable with it, you type db quit. Let's go back here. Let's try and run this thing again. Ooh, that was fast. Okay. Remember last class I tried to do that, got stuck with the memory allocation. And now look, the energy is almost constant. Or the amplitude is almost constant. It makes you believe, if you were only looking at some smaller number of oscillations, it would make you cook up the theory that perhaps this was trying to be constant amplitude and the mathematical solution would be constant amplitude. Now, if we want to get this more constant, we can do more accurate integration, and we're going to talk about that as the time goes on. Okay, any questions about the plotting? See this cute stuff I did as I made my name really big here in blue? So you can do things changing the font size and color of things when you label them. It's always a good idea to label your axis and so on. Okay, any more questions? Yes?
Do you have to still do the initialization on the top with what's not if you just call it 0?
The reason it's necessary is because of the way I organize this program, which is that inside this loop, the calculation part of the program, I just use x and x new. I didn't use the array at all. So I said, I know the present, let's look at the future. Then I'm going to call it the present, let's look at the future. I'm going to call it the present, let's look at the future. And on the side, I recorded the answer. So the reason I had to do that initialization is just to keep track of these variables here. I could have instead, if I organized this differently, and just kept all of the information in here and said, now I'm at t array sub 1, t array sub 2, I could have gotten rid of all of these variables, x new and x and so on, and my initialization could have just been for the first element in the array. So it would have been a little tidier in some ways, but actually this is a case where I think it's worth trouble to not be so tidy because it's just way easier to read these things without all the indices. Did I need to have these?
No, the one at the top, the above.
Oh, T array, so I messed this up. So this one I can get rid of now. Okay, it doesn't make any difference, yeah. Sorry. You're welcome. Any other questions? Okay, so now we want to get sort of more and more professional about this, more and more accurate about it. And if you look at this code and think about it, there's sort of three different things that are going on in this code. One is we're setting up a mechanics problem and telling MATLAB what we want to solve, setting up all these constants and so on. Another thing is we're writing what the differential equation is. And a third thing is we're implementing this method of solving the differential equation, which is called Euler's method. And what we'd like to do is separate out these three things. So we'd like one little program that has a differential equation in it, one little program that has Euler's method in it, and then one program that runs the whole thing. So it just gets a little logically complicated, but it becomes more compartmentalized. So the first step towards doing that, let me just do the first little step, is I want to put, say, the differential equation, just the differential equation, in a side little package. So if I want to put here, I'm going to calculate. So I'm going to have some function f, and I'm going to say f is equal to the right-hand side. I'm just calling it RHS. I can call it whatever I want. So don't be intimidated by the sequence of letters. And I'm going to say if I know the current position, and I know the current velocity, and I know the current time, I can calculate this right-hand side function. Which means down here someplace, I have to say what this function is. So it's a single text file, and this text file is containing two different blocks of code. So from the logical perspective, you can think of these as two different files, but you're allowed to put them in one place. So I'm going to have a function here, which is, and the name of the function is going to be right-hand side of x, v, and t. And then I'm going to have an end of the function, and in this particular case, I'm going to say the function f is equal to minus x. Now, if I want to pass in parameters to this thing, then it gets a little bit fancier, so I'm just going to leave that out for a second. Okay, now I'm going to run this, and what's going to happen? Who knows what's going to happen? It's going to crash because I have what? I have an extra equal sign. Now, where is that? Line 28. Well, that is bad. Okay, now that was a stupid trivial error. And the other error is, now you don't say it, somebody else say it. This function here, the top function, I didn't put an end on it. That's what he said, but that wasn't really the whole problem. The top function isn't even a function. So this is just another stupid, as far as I can tell, arbitrary MATLAB rule, is you're allowed to put two functions in one text file. You're not allowed to put a script file and a function file in one text file. So in order to make this run, I have to make this top thing, which was a script file, into a function file. Okay, so I need to call this function, and now I can just call it test1, and I think I don't need any more than that. So let's just see if this works again. Now, how can I tell if it worked or not if I'm doing exactly the same thing as I was before? I could put in a date or something like that, or I can change the differential equation. Let's change it from minus x to minus 2 times x. So even without going and looking at the error, I see if it's running. Ah, look, it ran fine. Okay, so I had to make the top thing a function instead of a script file. What's the difference between a function and a script file? Is when you're just messing around, like doing a homework problem with cross products and dot products, and you're just using MATLAB as a way of organizing your work, so that when you find a mistake, you don't have to do the whole calculation again. You just fix the one number, one line. Script files are good for that. What's nice about a script file is everything is public in a script file. In a function file, everything is private. So if I go here and go clear all, now I look at what's my list of variables. How do you say variables? Well, I can just look up here. See, there's no variables here. I go and run this function here. I close this thing. I go and run this function here. Go away, iClicker. I've supposedly run it. Let's make sure I ran it. Let's run it for more times. Look at the plot. There, running lots of times. Now, there's all these things I've calculated here. What's that? What's that? There's all these things I've calculated here. Let's see. I want to see what is k. Oops, no k. I want to see what is t array. Oops, no t array. In functions, everything is local. You can't get it on the outside. If you want to get it on the outside, you have to explicitly pass it or use a global command. That's good and bad. It's good for programming logic if you're writing a complicated program. It's bad if you're just messing around and trying to explore. So my recommendation is actually do the bad thing and use script files. Real programmers hate it, but just for messing around, learning things, use script files. And then when you're stuck and you want to do something like this, then use function files. Okay, any questions now? Okay, what if we want to check something like conservation of energy? We actually want to check the accuracy of this calculation. So we want to see, is energy conserved in this calculation? So what we can do is we can calculate the energy as a function of time. So at every time step, we can calculate the energy. So let's calculate the energy at the beginning of this thing. How are we going to do that? Well, let's just keep track of energy as a function of time. So I'll have a thing E tot. is equal to zeros of 1 comma n plus 1. So that's going to fill in my energy values. And I'm going to calculate the energy for this problem. Now, this is going to be really sloppy because the energy I'm going to calculate is only going to work for exactly this problem. In fact, I'm going to make it simpler than that. I'm going to go back to my earlier problem so that I don't make everything messy. So only this problem. If I want to put in the general problem, the general energy, I don't even know how to do that. If I want to make it somewhat more general, maybe down here, I'm going to have to calculate energy and so on. But now I just want to do a quick and dirty thing, calculate some energy. So I've calculated, I've set aside a place to keep the energy, and now I'm going to calculate it. In this particular case, E tot, the energy for a harmonic oscillator, don't say it out loud, but just think about what I'm going to type here. Okay, who has something in mind for me to type? Who does not? Just a minute, that means there's over 100 people who neither have something in mind or don't have something in mind in this room. Now, it seems like it's a logical thing. You either have something in mind or you don't. There's some kind of logical fallacy here. So let's try again. Who has something in mind? Raise your hand. Who does not? Raise your hand. Okay, so the energy, and we'll get into this either today or next time, is the potential energy plus the kinetic energy. In this case, I'm going to be really sloppy. The kinetic energy is 1/2 v squared. The potential energy is 1/2 the stretch in the spring squared. So this is mv squared over 2 plus kx squared over 2. So here we have the energy of the system as we go along in time. Put a parentheses here, end this thing down here, and now I have E tot, and now I have E tot. So here this was really E tot array. So I'm going to store this up here, and I'm going to store down here my E tot array sub I is equal to my E tot. And there's a little confusion about which time step I'm at. I could have done this after the calculation, before the calculation. So I've missed my first time step here. Should we get everything just right? If I'm going to get everything just right, I should put E tot. I should put this line down here where I calculate everything else. I should be V nu. It should be X nu. And I should put up here at the top, before I start the calculation, I should have a line that just mirrors this one and get the first one right. E tot array sub 1 is equal to, and then I'm going to put x0 squared plus v0 squared, and then I'm going to divide by 2. Okay. Now I've got everything lined up. And now when I go to here to do plots, I have this one plot here. And I can do a separate plot. So I'll call this figure 1. And then I'll do a second plot, which is a lot like it. And I'll call it figure 2. And that plot, I'm going to copy my syntax here. That plot, I'll put T array, and I'll put E tot array. And just so we don't get confused here, let's plot this in blue. And this is now going to be, hey, when I did that before, I had the labels wrong. Nobody fixed me on that. The Y label should have been position, and the X label should have been time. And that's on the website wrong, so I'll try to fix that. Okay, so now I'm going to have my X-axis label as time. Who saw that mistake and didn't tell me? Raise your hand. Okay, bad boy. And now I'm going to have total energy here. And this is Andy's second plot. Okay, now I see if it runs or not. And then I've got my total energy as a function of time. And it looks like it's increasing. Let's see, but it increases from what? Let's read carefully here. From 0.5 to 0.53. Didn't increase very much. If I go back here and spend more money on this, factor of 10 more money, and I run this again, I get a new plot. It's busy. Oh, did I have some horrible? Did I forget a semicolon someplace? Line 32. I forgot to do this, and then just printing actually takes more time than calculating, and so it took a long time printing, but it's done being busy. And now I look, instead of going from 0.5 to 0.53, it goes to 0.503. So this is a check of the accuracy. In this particular problem, the harmonic oscillator problem, we know something about the solution. Actually, we know the solution's sines and cosines, but even if we didn't know that, we know that the solution conserves energy. So we can check the accuracy of our numerical solution by seeing how well it conserves energy. And what we see is that it went from about 6% energy gain now down to about 0.6% energy gain by increasing the number of time steps or decreasing the step size. Is that clear? Not clear? Any questions about this? Okay, so now I think I'm going to stop MATLAB and go back to the world of chalkboard unless somebody has some questions. Yes? Is there a reason energy is increasing instead of decreasing? Yes, and I'll just show that to you on the chalkboard right now. Okay? It's increasing in a nice, smooth way too. Isn't that interesting? So even if I just do one oscillation, here's one oscillation. How do I do one oscillation? I just put 2 pi here, so it just goes around once. What? How did I do that? Now how do I get out of here? I've got, see that K, that horrible K? Remember this one. Most of your time in MATLAB is going to be spent not knowing things like this. dB quit. So you just want to accumulate these tricks, of which I do not know enough. Now look, just once around, and the energy increases in this totally smooth way. Sort of unusual, isn't it? Because the motion's oscillating, but the energy is just increasing like that. Okay, so I will try to explain that to you. And it looks like a straight line here. If we ran it for a long time, you'd see that it was actually an exponential increase in energy in time. Okay, so I go to off. System will shut down. Lights on. Screen up. So the question was, why does the total energy increase in time? And here's why. This is for the harmonic oscillator equation. For Euler's method, and the harmonic oscillator equation. So in general, it's not a feature that energy increases in time in numerical solutions, either of the equation or of the method. It depends on the equation and the method. So it's just this equation and this method we can understand. So the governing equation we had in this case was that x double dot was equal to minus x. It was really mx double dot equals minus kx in mechanics, but we said m equal to 1, k equals 1 to keep us closer to math land, to understand a mathematical example. Another way to write this equation is as x dot is equal to v, and v dot is equal to minus x. And this is the way that we are going to be thinking about differential equations. There's a part which is sort of the mechanics-y part having to do with acceleration, and there's a part which is just that the change in position is velocity. But really, the way we're going to think about this in the crystal ball sense is if we know the state of the system, that is, in mechanics and dynamics, the state is all the positions and all the velocities, we can predict, we know how things are changing, therefore we can predict the future. So we're going to think of this as one list of numbers, which later on we're going to call Z, which is all the positions and all the velocities. And by a mixture of kinematics and mechanics, we're going to know Z dot, and then we can predict the future. So we don't have to separate it in our mind, which is mechanics, which is kinematics. We just say I have rules which tell me the rates of change of all the variables. Okay, that's the starting point of view. So later on, we're going to think of this list of things. Later on is not so later, like next lecture. We're going to think of this things as Z, and we're going to think of this list of things as Z dot. And those of you who started to learn ODE 4.5 in section, this is you already learned this notation a little bit. Okay, with just two variables, we can plot things this way. We can look at t, and we can look at x, and we can look at some solution, say, given some initial condition. We can look at v of t and x of t. And the initial condition I've been using is position is 1 and velocity is 0. And so the velocity starts out 0. It gets more and more negative. Right here, when the position is at an extreme, is at 0, the velocity is most negative. Then when the position is at this extreme, the velocity is back through 0. Then when the position is at 0, the velocity is a maximum. And when we're at a maximum again here, we get down like this. So we can draw these two plots. But we can also do what's called a cross plot, where instead of plotting t on the x-axis and x and v on the y-axis, we draw this cross plot. In the world of differential equations, this cross plot has a special name. It's called the phase plane plot. But the meaning is we take an x value and a v value, put a dot over there, an x value and a v value, put a dot over there, and so on. And so instead of x changing in time and v changing in time, what we have is the position on this plane is changing in time. And for this particular motion and this particular differential equation, the motion is a circle in this plane. And that's this connection between sine waves and cosines and circles. Is as we move in time across here, we move from here to here to here to here. Time in this problem happens to be identical to arc length on this circle. And at any given time, the position is cosine of t, and the velocity is minus sine of t. So this function here, if we took the initial condition, x of 0 is equal to 1, v of 0 is equal to 0, this function is cosine of t, this function is minus sine of t, and we can see the relationship then between the circular motion in this phase plane and the cosine and the sine. But instead of just looking at the solution, we can also look at the ODE. So we can draw this phase plane again. And this is another way of thinking about the crystal ball, is that if we know the value of x and the value of v at some time, we know how both x and v are changing according to this equation. So if x is 1 and v is 0, then v dot is minus 1 and x dot is 0. So at this time, we know that whatever the change is, it's in that direction. And we can draw little arrows everywhere on this plane. In fact, we can draw them not just on the solution, we can draw them off the solution. So one way of representing the differential equation is by the set of arrows we draw on this phase plane. And this is the direction field. In Math 293, I think they made you learn a differential equation called D field. Is that correct? Do you use that program? Did you draw these pictures with computers in Math 293? Did you draw these pictures at all in Math 293? Okay, so a representation of the differential equation is I know the values, therefore I know the rates of change. Now I can look at velocity in the phase plane, which is the rate of change of these things, thinking of this as one coordinate and this is another coordinate. So here's the differential equation that we're trying to solve in this particular case. And we know that the exact solution is like this. If we did it exactly correct, this is the exact solution. And then we say, what are we doing with Euler's method? Well, with Euler's method, we calculate the velocity at one time, and we don't just go an infinitesimal distance and run the crystal ball millions of times, or billions, or an infinite number. We only run it 100 or 1,000 or 100,000 times. Let's just say we only run it a few times. What we're doing is we're taking a step in this direction. And where do we end up after one time step is here. Then we run the thing again. The nature of this direction field is this orthogonal to the position. And we go in that direction. And then we go orthogonal to this field in that direction. Then we go orthogonal to the field in that direction. And then we go orthogonal to the field in that direction. And what you see is that this Euler method spirals out. And what does that give you? It gives you this increase in amplitude. And that increase in amplitude corresponds to an increase in energy. Okay, so look at this for a minute, ask me a question, and then I can go on. Especially the person who asked me the question to start with. Who asked the question to start with? And you're the same guy who noticed that I put time on the wrong axis? Okay. Comes out about even then. But look out in the future. In case you didn't understand the accounting, plus credit for asking a question, minus credit for not pointing out a mistake. Okay. Ask anything unclear about this? This is clear. Euler method clear. Phase plane clear. The way I write the second order equation is first order equations clear. The connection to the harmonic oscillator clear. Yes?
Why does spiraling out
This is the variable x, and this is the variable v. So at any instant in time, what I'm looking at is the values of x and v. So if I keep spiraling this around until I get to here, then after I've done one oscillation, I'll have a new value of x, which is bigger than the last value of x. And then the next time around, I'll have a bigger value of x, and so on. So the radius of this thing is proportional to x squared plus v squared, or the square root of that. And spiraling out means the quantity x squared plus v squared is getting bigger, which means every time it crosses either the x or the v axis, the x or v axis values are bigger. Who asked the question? Does that address your question?
What?
Does that address your question?
Yeah.
You're happy with that?
Yes.
Okay, another question? Okay. So let's look at the harmonic oscillator. What we had was the governing equation, which came from free body diagram and from linear momentum balance. Gave us a differential equation, which was that mx double dot is equal to minus k x. Now we could try to solve that equation, and you've learned how to solve it, but you're supposed to know the solution, sines and cosines, faster oscillations if k is bigger, slower if m is bigger. But there are things you can figure out about this without the analytic solution, without memorizing it, without deriving it. What can we figure out? We can actually figure out the curves as a function of time by numerical integration. But we can figure out things, other things, for example, conservation of energy. Now, conservation of energy, historically in mechanics, is not a axiom. It was something that was originally derived. So we start with the equation F equals ma, and the question is, can we derive conservation of energy? And we can, and the derivation goes like this. We take this equation here, we multiply both sides by x dot, and it gives us mx dot x double dot equals minus k x x dot. Then what you notice is that this expression here is d by dt of 1/2 x dot squared. And what you notice is that this is d by dt of 1/2 kx squared. How do you notice that? Because you've seen it in class about 5 times, and people have derived this thousands of times, so you make that lucky guess. You say if you want to get here deductively, it's maybe not so obvious that you could do such a thing. And in hard problems, you don't even know if there is a conservation law or isn't a conservation law, and there's no real general rule for doing this derivation. But for these simple problems, here's the trick. You multiply by x dot, and you notice this fact. Why is this fact true? If we differentiate this as 2x dot times the derivative of x dot with respect to t, which is x double dot, the 2 and the 1/2 cancel, and we get this. Same idea right here. Take the derivative of this, we get 2kx, multiplied by half is kx. Then we have to use the chain rule times the derivative of x with respect to t, so times x dot. What does that tell us? It tells us that d by dt of a quantity we'll call ek is equal to minus d by dt of a quantity we'll call ep. And this thing we'll call the potential energy. This thing we'll call the kinetic energy. In this particular problem, this thing is 1/2 mv squared. This thing is 1/2 kx squared. Then what does that tell us? It tells us that d by dt of a thing we'll call the total energy is equal to 0, which tells us that the total energy is equal to a constant. And what do we mean by the total energy? Is we mean EP plus EK. So from this, we derive that the energy is constant, which is what we expect to see in the numerical solution, or approximately if it's accurate enough. Okay, I end on time today. If you have questions, ask them next time.